Hi everyone, this is Louise here. Today we are going to go through the Chemistry Paper 1 Multiple Choice, May-June 2020, Paper 1-1. Okay, so next we're going to go to question 1. Okay, question 1. Okay, ethene can be oxidized to form epoxy ethane. Okay, so this equation here. Okay, so we can see that this is equilibrium. Okay, so this is an equilibrium. Okay, right, and another thing we need to pay attention, okay, is this enthalpy of change here. Okay, so we can see that this is exothermic reaction. Okay, and regarding the pressure, okay, so we can check the total number of moles, okay, of gas on each side. Okay, so here on the left hand side is 1 mole, okay, and 0.5 moles. Okay, and then right hand side is 1 moles. Okay, so so on the left hand side total is 1.5 moles. Okay, on the right hand side total is 1 mole. Okay, so in terms of pressure, okay, so what happens when we increase the pressure? Okay, the equilibrium, okay, will attempt to reduce the pressure. Okay, so in order to reduce the pressure, the equilibrium will move to the right hand side. Okay, which will increase the yield. Okay, so for pressure, so we want the high pressure situation. Okay, so for temperature, okay, we know that it is an exothermic reaction. So meaning when we increase the temperature, the equilibrium will try to decrease the temperature. Okay, so the way it does that is by performing the reverse reaction. Okay, so yield will decrease. Okay, so meaning what we want to do here in order to increase the yield is to decrease the temperature. Okay, when we decrease the temperature, the equilibrium will try to increase the temperature. Okay, so this will favor the forward reaction. Okay, so which will increase the yield. Okay, so in this case here, okay, the reaction conditions that we want is the decrease temperature and increase pressure. Okay, so answer is A. Okay, let's take a look at question 2. Okay, so cobalt form the positive ion. Okay, so this ion here. Okay, so we are looking for the oxidation number of cobalt. Okay, so this is quite straightforward. Okay, so here we know that the overall charge is +1. Okay, so and we know that ammonium, okay, sorry, ammonia. Okay, so ammonia is 0 charge. Okay, so we can ignore that. So we take cobalt. Okay, we know that chloride is -1. Okay, so chloride, um, cobalt plus 2 units of chloride. Okay, each one -1. So overall equal to negative +1. Okay, so CO minus 2 equals to +1. So oxidation state of CO is 2 plus 1. Okay, so it's +3. Okay, so answer is C here. Okay, so when considering 1 mole of ethene, okay, which row describe both the hybridization of the atomic orbitals, okay, in the carbon atoms and the overall bonding? Okay, so first we need to take a look at the structure of ethene. Okay, so it's alkene. Okay, so this is the basic structure. Okay, so and we know that all of the single bonds, okay, they are sigma bonds. Okay, so we know that we're going to have, okay, 1, 2, 3, 4, 5 sigma bonds. Okay, and then we're going to have 1 pi bond. Okay, so basically the second bond is going to be a pi bond. Okay, another thing we need to look at is the hybridization. Okay, so we can take a look at the shape here. Okay, the shape is trigonal planar, okay, around the carbon. So trigonal planar corresponding to sp2 hybridization. Okay, so the answer here is B. Okay. Okay, question 4. Okay, so we are looking at the combustion. Okay, so we are looking at the combustion of ethane. Okay, burning in oxygen. Okay, at pressure 101 kilopascal and temperature of 200 degrees Celsius. Okay, so so it's asking about the total volume of gas present when the reaction is complete. Okay, so the first thing we need to do is we need to work out the equation. Okay, so we can write up the equation. So we know that the starting material is this ethane here. So it's C2H6 plus, okay, oxygen, okay, plus carbon dioxide, okay, plus water. Okay, so we know that these are the products of a standard combustion. Okay, so now we need to balance it. Okay, so the first thing we can start with is so we have two carbons here. Okay, so two carbons here, so meaning to balance we're going to have two carbons here. Okay, and then hydrogen is 6 here. Okay, so we're going to make it 3 here to make it 6 hydrogen. Okay, so we count number of oxygen here. Okay, so is 4 oxygen. Okay, here 3 oxygen. Okay, so in total we're going to need like 7 oxygen here. Okay, but because this is O2, okay, to make the numbers easier, okay, so if we wanted to keep it this way, we can make it 7 over 2. Okay, but to make the numbers easier to handle, what we're going to do is we're going to multiply by 2. Okay, everything. Okay, multiply by 2. Okay, so that the numbers going to be easier to handle. Okay, so 2, okay, 7, 4, and 6. Okay, so this is fully balanced. Okay, so now we can check the ratio, okay, of all of the um, substances. Okay, so we know that it's going to be 2 to 7, okay, 2, 4, 2, 6. Okay, so we know that in under the gaseous condition, okay, so the volume of gas is representing the number of moles. Okay, so we can use the volume of gas directly as the number of moles. Okay, so we start with 10 cm cube, okay, of this ethane here. Okay, so from here we can work out the amount of oxygen needed. Okay, so in this ratio here, so what we can do to work out the oxygen is we take 10. Okay, so first we divide by the 2, next we multiply by the 7. Okay, so we know that here we're going to need 35 cm cube of the oxygen. Okay, but if you look at the question here, okay, actually provided 45, so we know that we're going to have a remaining, okay, 10 cm cube. Okay, 45 minus 35. Okay, so for CO2 and H2O, okay, so we can work out the volume accordingly. Okay, so we know that CO2 is twice the amount of the ethane. Okay, so it's going to be 20 cm cube. Okay, and then the water is 3 times, okay, the amount of the ethane, so it's going to be 30 cm cube. Okay, so at the end of the reaction, the gas that we expect to be present is this 20 cm cube of the carbon dioxide, okay, 30 cm cube of the water and 10 cm cube of the remaining unreacted oxygen. Okay, so if we add all of them together, it's going to be 20 plus 30 plus 10, so total is 60 cm cube. Okay, so the answer is D. Okay. Okay, question 5. Okay, two reactions are shown. Okay, these two reactions here. Okay, so these two reactions are associated with which energy change below. Okay, so actually we need to see carefully, okay, the definition, okay, of each one. Okay, so enthalpy of atomization is for when, okay, 1 mole of, okay, of atoms, okay, are produced. Okay, so if we look at this case here is 2 moles of atoms produced, so we know that enthalpy of atomization is incorrect. Okay, how about bond energy? Okay, so bond energy is when, okay, 1 mole of, okay, bonds, okay, broken. Okay, so this is 1 mole here. Okay, so this is correct. Okay, all right. Okay, so next we consider the second one. Okay, so is this enthalpy of combustion, okay, or enthalpy of formation? Okay, so we need to see carefully. Okay, so it is not formation. Okay, because formation, the starting materials, okay, the starting materials, okay, must be elements. Okay, so if you take a look here, this CO is a compound. Okay, so it's not an element. Okay, so this is not a enthalpy of formation. So it is a combustion. Okay, so combustion is for when 1 mole of substance, okay, 1 mole of substance, okay, is reacted. Okay, so this is correct, so the answer is C. Okay, take a look at this diagram here. Okay, Boltzmann energy distribution of curves. Okay, take a look here. Okay, so which letter on the axis represent the most probable energy, okay, for the molecules of the same sample, okay, of gas at a lower temperature? Okay, so first we can identify the two axes. The y-axis is this is amount. Okay, so how much of it? Okay, this is energy. Okay, so we can identify, so this one is actually the um, low temperature. Okay, low temperature condition. This is the high temperature condition. Okay, so it's also corresponding to the low energy, okay, and high energy condition. Why? Because the high energy condition, okay, it has a greater proportion, okay, of molecules, okay, in the higher energy region. Okay, so when the temperature is low, okay, so most of the molecules are concentrated in the low energy region. Okay, so we are looking at this curve here. Okay, and the one, okay, axis represent the energy. Okay, so we are concerned about the energy, and then the curve with the lower energy. Okay, so we are looking at this point here. Okay, question 7, what are the units of Kp, okay, for the reaction shown? Okay, all right, Okay, so we know that, okay, so this is solid, okay, so this is not included, okay, in the equilibrium constant, okay, the equilibrium constant equation, okay, so these are gases, okay, so and the unit is pascals, okay, so we know that the equation for the equilibrium constant is the reactants, okay, over, sorry, is products over reactants, okay, so is, so we are comparing the proportion, okay, between products and reactants, okay, and we are looking at the concentration or the pressure, okay, so the solid is not included because the concentration or the pressure of the solid stays pretty constant, okay, over time, so it's excluded, okay, so we put the pressure, okay, of the hydrogen gas multiply the pressure of the CO gas, okay, over the pressure of the water, okay, so all of them in gaseous form, and then we know that the unit for all of them is pascals, okay, so pascals, 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 okay, so pascals multiplied by pascals over pascals, okay, so when we cancel out, okay, so we find that the final answer is just pascals, okay, so the unit for this equilibrium constant is simply pascals, okay, okay, take a look at next question. Okay, so in this question here, okay, we need to balance, okay, this redox equation here, okay, so to balance this redox equation, okay, so what we need to do, okay, we need to, okay, so basically we need to start with the half equations, okay, okay, let's take a look here, okay, so how do we work out the half equations, okay, so we identify the species, okay, so we can see that chromium, okay, so some changes of the chromium, okay, and some changes on the vanadium, okay, so the first thing we can do is we can work out the changes in the um, oxidation number, okay, so for chromium as usual, okay, so we take 2 chromium, okay, plus 7 oxygen, so oxygen is negative 2, so equal to negative 2 here, okay, so once we rearrange, okay, so we can get 2 chromium equals to 14 minus 2, so 2 chromium equals to plus 12, okay, so the oxidation number of chromium is plus 6, okay, so we know that initial is plus 6, okay, so we can use the same method to work out the rest, okay, so the final chromium here is straightforward, it's just plus 3, so we can see that a reduction, okay, occurred here, okay, so for vanadium starting is plus 2, okay, so the final one is V plus 3 negative 2 of oxygen equals to negative 1. Okay, so vanadium oxidation state is 6 minus 1. Okay, so it's plus 5. Okay, so we can see that there is oxidation happening here. Okay, so first we list out, okay, the species that are involved, okay, in each half equation. So for the chromium, okay, for the chromium one is Cr2, okay, O7, okay, 2 negative, okay, so it becomes, okay, Cr3 plus, okay. So the first thing we can do here is that we know that we have 2 chromiums here, so plus 6 plus 6, so the total charge on the left hand side is plus 12, okay, for the chromium, okay, and then so two chromiums here, so we need to balance by two chromiums here. So the total positive charge here is 2 times 3, which is plus 6. Okay, so you can see here, going from left to right, okay, so it's a reduction. Okay, so a reduction, we need to balance both side charges. Okay, to balance the both side charges, okay, we plus 6 electron on the left hand side. Okay, so now plus 12 plus the 6 electron, we get a plus 6. Okay, so which is equal to the right hand side. Okay, so next we want to balance the oxygen. Okay, so to balance the oxygen, what we can do is we add 7H2O here. Okay, so now both sides we have 7 oxygens, but now we have the extra hydrogen. Okay, so we balance by adding 14 protons, okay, on the left hand side. Okay, so the first half equation is balanced. Okay, so now we look at vanadium. Okay, so vanadium we start with V2 plus, okay, and then it becomes, okay, VO3, okay, negative. Okay, and then the starting oxidation number is plus 2. Okay, here it becomes plus 5. Okay, so meaning here we need to add 3 electrons, okay, to balance the charges. Okay, so next we need to add the water to balance the oxygen. Okay, so 3 moles of water here, okay, and then to balance the hydrogen, okay, so 6 protons here. Okay, so now what we can do is we can compare the number of electrons. Okay, so to finally balance both equations, combine the two equations together. Okay, so what we need to do is to make the number of electrons equal. Okay, so the way to do that is we take this equation here and then we multiply by 2. Okay, so when we do that, the result is, okay, 2V2 plus, okay, plus 6H2O, okay, becomes 2VO3 negative plus 6 electron, okay, plus 12 protons. Okay, so now we are ready to combine, okay, the equation. Okay, so we can check one by one. Okay, so first, okay, we look at the protons. Okay, 14 on the left, okay, 12 on the right. Okay, so means overall, okay, 2. Okay, means overall 2 on the left hand side. Okay, okay, chromium. Okay, so chromium is here. Okay, just 1 unit. Okay, so the number is 1 here. Okay, and then on the right hand side, okay, this chromium is 2 units here. Okay, so this is 2. Okay, and then the water, okay, we take a look the water, so it's 7 on the right hand side, okay, 6, okay, on the left hand side, so overall, okay, 1 unit, okay, on the right hand side. Okay, so the electrons, they basically cancel out. Okay, 6 and 6. Okay, and then here 2 vanadium, okay, and 2 vanadium here. Okay, so now we work out the coefficients, okay, for each terms there. Okay, okay, so these are all of the coefficients. Okay, so if we look at the question here, it's asking for A to B. Okay, so A to B is simply 1 to 2. Okay, so the answer is B. Okay, 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 next question. Okay, so you have a sample of gas here. Okay, so you have some conditions. Okay, so how many grams? Okay, the pressure, okay, and also the temperature, okay, they need the volume, okay. So so we can immediately relate that. So this is related to the ideal gas equation, okay. So we know that the ideal gas equation is PV equals to nRT, okay. So in this case we need the volume here, so we can simply rearrange, okay. So volume equals to nRT over P, okay. So now we can input the available information here, okay. But before that we need to make some changes, okay. So for example, the temperature, okay, so it needs to be in Kelvin, okay. So this is what we need to pay attention when we use the ideal gas equation, okay. We need to make sure that the units are correct, okay. So to change the Celsius to Kelvin, we take 12 plus 273, so that is 285 Kelvin, okay. And then okay, so this one is number of moles here, okay, n is the number of moles, okay. So this 0.2 grams we need to change to the number of moles, okay. To do that we need to know the atomic mass, okay, of argon, okay. So that is, okay, we can get from the periodic table 39.9 gram per mole, okay. So the number of moles is equal to 0.2 gram, okay, over 39.9 grams per mole, okay. So that's equal to 0.005 mole, okay. So okay, the pressure is fine, it's in the correct unit, okay. So now we are ready to input everything, okay. So the number of moles is 0.005, okay, multiplied by the constant R, which is 8.31, okay. So we can get from the data booklet, okay, 285 temperature over pressure, okay. So which is this one here, okay. So when we complete the calculation, we will get okay, the volume in meter cube, okay. So this is the one we need to pay attention, okay. So 1.187, okay, times 10 to the power of negative 4, this is meter cube, okay, because this ideal gas equation here, okay, the unit for the volume is in meter cube, okay. So we need to change that to the cm cube, okay. So the conversion factor for meter cube, okay, to cm cube is 1 million, okay. 1 meter cube equal to 1 million cm cube, okay. So we can input that, okay. Okay, okay. So once we done that, we will get 118.7, which is round up to 190 cm cube, okay. So the answer is D, okay. Okay, so the next question, which pair, okay, which pair has the same number of unpaired electron, okay. So when we're talking about the unpaired electron is when we have the orbital, okay, when we have two electrons, so this is pair, okay. So when we have a single electron, so it's unpaired, okay. So now for each of these species we need to work out the electron configuration, okay. So okay, and then once we know the electron configuration, we can work out the number of unpaired electrons, okay. So for aluminium is neon, okay, with 3s2 and 3p1, okay. So we can see there is one unpaired electron here Okay, so it's 1 for aluminium. Okay, for copper 2 plus is, okay, argon 3d9. Okay, so when we have 3d9, the d orbitals, okay, we have 5 orbitals, 1 2 3 4 5. Okay, 3d9 is 9 electrons, so 1 2 3 4 5 6 7 8 9. Okay, so this also have 1 unpaired electron. Okay, so basically this is the answer. Okay, same number of unpaired electrons. Okay, so for the rest you can work them out in the same way. Okay, so for B is 0 and 3. Okay, 0 and 2. Okay, 5 and 0. Okay, so you can work them out by first determining the electron configuration, and then work out how many unpaired electrons are there. Okay, so I will write down the rest, okay, for your reference. Okay, 4s2, so no unpaired electrons. Okay, so this is also argon, 4s2, also no unpaired electrons. Okay, so argon, okay, 3d5. Okay, so we know that in the 5 orbitals, okay, okay, so it will fill up singly first. Okay, so 5 unpaired electrons. Okay, so for chromium is Ar. Okay, 3d3. Okay, so 3 unpaired electrons. Okay, so for nickel is Ar, 3d8. Okay, so if you do the same thing, okay, 1 2 3 4 5 6 7 8. Okay, so 2 unpaired electrons there. Okay, so so oxygen is also no unpaired electrons. Okay, so this is the idea there. Okay, next. Okay, decomposition of the ammonium chloride. Okay, so a total of these molecules of gas form. Okay, so for this question, the first thing we can do here is to write down the equation. Okay, for this reaction here. Okay, so ammonium chloride. Okay, so this is ammonium chloride. Okay, decomposes into ammonia. Okay, and HCl. Okay, so so this is fully balanced. The first thing we can notice is that the ratio between ammonia and hydrochloric acid is 1 to 1. Okay, so and we know that total products is this number of molecules. Okay, so meaning this number of molecules is distributed evenly between the two, because the number of moles is the same. Okay, so each of them takes half. Okay, so means is 1.2 times 10 to the power of 21, and then 1.2 times 10 to the power of 21. Okay, the next thing we need to notice is in the question, so it's asking for how many hydrogen atoms. Okay, so so we can see that for ammonia, each mole of ammonia there are 3 moles of hydrogen. Okay, and then each mole of HCl there are 1 mole of hydrogen. Okay, so meaning for this number of moles here, it needs to times 3 to get the number of moles of hydrogen. So for this one you need to times 1 only. Okay, so because it's 1 mole of hydrogen. Okay, so meaning you end up with total of 4 moles of hydrogen times 1.2 to 10 to the power of 21. Okay, So the final answer is we expect, we expect to get 4.8 times 10 to the power of 21, okay, hydrogen atoms, okay, present, okay. So the answer is C, okay. Okay, question 12, okay. So this one is identification of anions, okay, reaction. Okay, so we take a look first, okay. A mixture of sodium chloride and sodium iodide, okay. So basically, when we, okay, we take a look next. Excess equals silver nitrate, okay. When we see the silver nitrate, we know that is the identification of the halogens, okay, chloride or iodide, okay. So we know that when chloride, okay, we have chloride and iodide, okay, added with silver nitrate, okay, we're going to get silver, okay, we're going to get silver chloride, okay, and silver iodide, okay. Silver chloride is white precipitate, okay. Silver iodide is yellow precipitate, okay. So this is the precipitate X, okay. So which is a mixture of AgCl and silver iodide, okay. So the next thing we do is we add the concentrated ammonia, okay. So we know that this is the test to differentiate, okay, between chloride and iodide, okay. So we know that silver chloride will dissolve, okay, in NH3, okay, but silver iodide is insoluble, okay. So basically we expect the final precipitate, which is Y, okay, will contain, okay, silver iodide only, okay, because the silver chloride is dissolved, okay, in the concentrated ammonia, okay. So we take a look at the answer options one by one, okay. X is pure white color, so this is wrong, okay, because we know that it's a mixture of silver chloride and silver iodide, so it should be kind of maybe light yellow, okay. X is pure silver iodide, we also know it's incorrect, we know that it's a mixture, okay. Y is pure silver chloride, we know that this is incorrect because we know that the silver chloride already dissolved, so we are remaining with silver iodide, okay. We know that Y is yellow, so this is correct because it is silver iodide, okay. So the answer is D, okay. Number 13, okay. So 6.9 grams, okay, of ammonium salt is heated with an excess of aqueous sodium hydroxide, okay. Okay, so the volume of, so it produces ammonia, okay, and this is the amount, okay, 2.51 dm cube, okay. So the first thing we can do is, okay, the ammonium salt, okay, we want to identify which ammonium salt, okay. So it could be one of A, B, C, D here, okay. So the first thing we can do is we can work out the number of moles, okay, because we have 6.9 grams, okay. So we take 6.9 gram, okay, divide by this 4 molar mass here, okay, so we can get the number of moles, okay, for each of them, okay, divide, okay, mr, okay, okay. So if you done that, you will find the following number of moles, okay, 0.0719, okay, 0.129, okay, 0.0863, okay, 0.0522 moles. Okay, so that's the first thing we can do. Okay, and then the next thing we can do is we can we can write up the reaction equation. Okay, so the equation should be reaction with ammonium salts. Okay, so I only write about the ammonium salt. Okay, and sodium hydroxide, I only include the hydroxide because the sodium is not changed, it's just a spectator ion. Okay, so the products are okay, ammonia, okay, plus water. Okay, so once the equation is done, we can take a look of the ratio. Okay, the expected ratio. Okay, so if we start with 1 mole of each, okay, let's say if we start with 1 mole of each, okay, we know that ammonium is +1. Okay, ammonium is +1, the charge. Okay, so the charge is +1, and then carbonate is 2 negative. Okay, chloride is -1, nitrate is -1. Okay, and sulfate is 2 negative. Okay, so you can see to balance the charges, so you need 2 units of ammonium here. Okay, so this is still 1, this is still 1, and this is also 2. Okay, to balance the charges. Okay, so this is important because you can see here, every 1 mole of ammonium salt reacted, you will get 2 moles of ammonia here. Okay, because you have started with 2 moles of ammonium here. Okay, so we can check accordingly. So this should be 1 and 1. This should be 2 also. Okay, so with this information here, we can use this number to work out the number of moles, okay, that we expected for ammonia. Okay, so this one need to times 2. Okay, so times 2, we end up with, okay, 0.1438 mole. Okay, so this just stays the same, 1 to 1. Okay, 0.129 moles. Okay, so this is stays the same, 0.0863 moles. Okay, so this is twice, okay, because this is 2 moles. Okay, 0.1045 mole. Okay, so this is what we expect, okay, for each ammonium salts. Okay, so the actual amount of ammonia produced is this. Okay, so this one we can multiply with the molar volume, okay, to get the number of moles. Okay, so this is 1 mole equal to 24 dm cube. Okay, so 2.51 dm cube. Okay, so if we calculate that, we would get 0.1046 mole. Okay, so which matches with, okay, this one here. Okay, so we can conclude that the ammonium salt used, okay, is the ammonium sulfate. Okay, next. Okay, excess of MgO is shaken with water. Okay, and then the resulting mixture filtered into test tube P. Okay, barium oxide, okay, also shaken with water. Okay, and then resulting mixture filtered into test tube Q. Okay, so first we are concerned about the reactivity. Okay, so which one is more reactive? Okay, so if we compare, okay, magnesium and barium, okay, both of them in group 2, okay, we know that for group 2, the reactivity increases, okay, down the group. Okay, because the radius increases, okay, the atomic radius increases, okay, so the valence electrons is, it could be lost, okay, easily, okay. So another thing we can conclude is the BaO bond length is longer, okay, so it's a weaker bond, okay, so it reacts, okay, reacts, okay, easily, okay. So from here, okay, we can conclude that the more reactive one is the barium oxide, okay. So because it is more reactive, okay, so when it reacts with water, okay, because it's more reactive, when it reacts with water, okay, so it will form the hydroxide, okay, and form the, okay, the OH negative, okay. So the more reactive, the more hydroxide it will form, okay. So it will have a higher pH, okay. So barium oxide is the Q, so we expect the Q to have the higher pH, so we expect P to have the lower pH, so answer is A, okay. Okay, 15, okay, element that has a giant structure, okay, so we are considering 4 elements here, okay, um, aluminum, okay, magnesium, okay, silicon, and phosphorus, okay. So so basically this is metal, okay, and silicon. So metal is having metallic lattice, okay, so this one is considered as giant structure, okay. So silicon has the same structure as the carbon, okay, so it has a diamond structure, so which is also giant lattice, okay. But phosphorus is present as the molecules of P4, okay, so it's not a giant structure, okay, so we can exclude phosphorus at this point, okay. Fluoride of Z, okay, so now we are left with aluminum chloride, okay, magnesium chloride, okay, and silicon chloride, okay. React with water to give a solution with pH less than 5, okay. So so we know that magnesium is um, alkaline, okay, so basically it will not, okay, produce pH less than 5, okay, so the answer is aluminum and silicon, okay. So basically aluminum and silicon will react with water to form acidic solution, okay. Okay, question 16, okay. Okay, so we are looking at these three compounds here, okay, okay, and their characteristic, okay. So we know that metal oxides, okay, in general they are basic, okay, or alkaline, okay, okay, non-metal oxide, okay, okay, like CO2, okay, SO2, they are acidic, okay, so they dissolve in water to form acidic solution, okay. So sodium is metal, so it forms basic oxide, okay. Giant ionic, okay, lattice, yes, okay. High melting point and reacts with water, yes, okay. Aluminium oxide, we know that is amphoteric, okay, so basically it reacts with both acid and alkali, so this is no. Giant ionic, yes, ionic compound, okay. Low melting point, no, okay. Ionic compounds, they have very high melting point. No reaction with water because aluminum oxide is very stable and is insoluble in water, Okay, so now we are left with these two options here. Okay, okay, silicon dioxide. Okay, simple molecular, no. Okay, so silicon dioxide has the same structure as the diamond. Okay, so which is a giant structure. Okay, no reaction with water, yes, because it is insoluble in water. Okay, so the answer is D. Okay, 17. Okay, 0.25 grams of anhydrous, okay, magnesium nitrate heated strongly. Okay, so this is decomposition of magnesium nitrate. Okay, so okay, so the equation is like this. Okay, so is 2 mg, okay, NO3, okay, plus, okay, so basically it decomposes into 2 MgO plus 4 NO2, okay, plus O2. Okay, so if you check the, okay, so in the question they're asking about the total volume of gas produced. Okay, so first we can take a look. Okay, so here produce, so this is solid, so we don't consider this one. So this is gas, this is gas. Okay, so we have 4 moles of nitrogen dioxide and 1 moles of oxygen. So we expect to produce 5 moles of gas, okay, for every 2 moles, okay, of magnesium nitrate reacted. Okay, so from here we can work out how many moles of magnesium nitrate. Okay, to do that we need to work out the molecular mass, okay, of magnesium nitrate. Okay, so that's 24.3 plus, okay, 2 units of nitrogen, okay, 14 here, okay, and 6 units of oxygen. Okay, so total should be 148.3 grams per mole. Okay, so we take this 0.25 divided by 148.3, we can get okay, so is 0.0168 moles. 0.0168 moles. Okay, so we know that Mg and O3, okay, versus the gas is 5 moles. Okay, so it's 2 versus 5. Okay, now we know that MgNO2 is 0.00168. Okay, so to get the number of moles of gas, basically we take 0.0168 divide by 2 and then multiply by 5. So the number of moles of gas is 0.004215. Okay, so this is equivalent to, okay, so we multiply with the molar volume. Okay, so 0.004215 moles. Okay, okay, multiply with the molar volume. Okay, which is 24 dm cube, okay, per mole. Okay, so now we need to change the dm cube, okay, into cm cube. Okay, 1 dm cube equals to 1000 cm cube. Okay, so if we evaluate this, we will find that the final volume is 101.16 cm cube. Okay, so meaning the answer is C. Okay, okay, question 18. Okay, astatine, okay, below iodine. Okay, so which statement is most likely to be correct? Okay, so okay, so we can take a look one by one. Okay, all right. Okay, so the first thing we can say is AgATS, okay, reacts with excess dilute aqueous ammonia to form a solution of soluble complex. Okay, so okay, so we can compare with um, silver chloride here, okay, silver bromide, okay, silver iodide going down the group 17, okay, and silver astatine, okay. So okay, so actually from the okay test of anions, okay, okay, we know that actually silver iodide is insoluble, okay, and then silver chloride is soluble, okay, so we can conclude that silver astatine is insoluble, okay, so this is wrong, okay, okay, so KCl, okay, react with KCl, so this is the displacement reaction, okay, so astatine replacing the chloride ion, okay, so we know that this can only happen, the displacement can only happen if astatine is more reactive than the chloride, basically is displacing the chloride, okay, but in this case astatine is less reactive than chloride because we know that going down group 17, okay, the reactivity of the elements decreases, okay, because the atomic radius is increasing, okay, so on the outside there are 7 valence electrons, so as the radius getting bigger, so Cl, the radius is smaller, okay, so the valence electron, okay, so 7, okay, so 7 valence electron, and then astatine has a much bigger radius, so in order to form the octet, they need to plus 1 electron. But for astatine, the distance is quite far, so it's more difficult for it to attract the extra electron. So basically, reactivity decreases going down group 17. Okay, so astatine cannot displace chloride. Okay, and then in this case here, okay, so KCl is a salt, okay, or KAT is a salt, okay, so basically it does not react with dilute sulfuric acid, okay, so meaning the answer is D, so this is the one that is possible to happen, okay, because we know that actually sodium chloride, okay, can react with concentrated sulfuric acid, okay, so if it can happen with sodium chloride, so it is likely that the same thing can happen with sodium astatine also, okay. Okay, question 19, okay. Okay, so this one we are talking about, okay, which one has the highest melting point, okay, so okay, so this is ionic compound. Okay, so we expect the MgCl2 to have the highest melting point. Okay, so meaning we are left with these two options here. Okay. Okay. So next we compare CCl4 and PCl5. Okay. So PCl5 actually have a higher, okay, molecular weight. Okay. So meaning the okay, the van der Waals, okay, the van der Waals, okay, forces stronger, okay, so that's why, okay, so it will have a higher, okay, melting point, okay, okay, because the molecules are more strongly attracted to each other, okay, so the answer is A, okay. Okay, 20, okay, okay, let's take a look of this compound X here, okay, okay, so what we need to do here, we need to work out the molecular formula, okay, we need to check the observation with Fehling reagent, okay, okay, so to work out the molecular formula, first we need to work out how many carbons are there, okay, so 1, 2, 3, 4, 5, 6, 7. Okay, that's fine. 7 carbon, all 7. Okay, 1 oxygen, all 1. Okay, so the next thing is the number of hydrogen. Okay, so this one we can work out by knowing two things. Okay, first, okay, carbon form 4 bonds. Okay, and the bonds with hydrogen, okay, not shown. Okay, so if you take a look here, okay, so you have all of the carbons here. Okay, so this carbon only form 1 bond so far, so we expect the rest is 3 hydrogen. So this one also 3. So this one already have 3 bonds, so 1 hydrogen. Okay, so this one already have 2 bonds. We expect 2 more hydrogen, 2 more. Okay, so this one already form 4 bonds, so there will be no hydrogen. So this one have 3. Okay, so if we add them all together, we'll find that the hydrogen equals to 14. Okay, so the formula is this. Okay, so we are left with 2 options here. Okay, so this Fehling reagent is a test for it's a test for to differentiate aldehyde and ketones. Okay, so we can see that this one is a ketone group here. Okay, so this is a ketone group. Okay, because both side is carbon. Okay, carbon here and carbon here. Okay, so for aldehyde is one side is hydrogen, one side is carbon. Okay, so the Fehling reagent aldehyde will react with the Fehling reagent, but the ketones will not react. Okay, so in this case we expect no change. Okay, so answer is A. Okay, 21. Okay, so which one is correct? Okay, so we want to check whether each of them, okay, excuse me, they are isomers or not. Okay, so the simplest thing we can do is to check the number of carbons. Okay, so if they don't have the same number of carbons, so they are definitely not isomers. Okay, so if they have same number of carbons, so we can check the rest. Okay, number of hydrogen and the number of oxygen. Okay, so we can sketch out the skeleton. Okay, so for this one here, so propanoic, so is 1, 2, 3 carbons. Okay, so with the COOH there. Okay, so propanoic acid group, and then the 2 metals, okay, on the second carbon. Okay, so so this is 5 carbons. Okay, so this is 5 carbon. Okay, propyl metanoate. Okay, so propyl metanoate, so is propyl 1, 2, 3, okay, carbon, and then oxygen joined to the metanoate. Okay, so 1 carbon here. Okay, and then okay, and okay, so um, yes, so just like this. Okay, so this is the metanoate. Okay, so this is 1, 2, 3, 4 carbon. Okay, so this is 4 carbon. Okay, so this one metal is 1 carbon, butanol is 4 carbon, so this is 5 carbon. Okay, so this is 6 carbon. Okay, so this one not same number of carbons, so we can exclude. This is also not same. Okay, how about this one? Butane is 4, dimethyl is 2 carbon, so total 6. Okay, so this one pentan is 5, so this is also not same. Okay, so we are left with this. So this is butane is 4, metal is 1. Okay, so total is 5. This is also 5. Okay, so without working out the rest, we can conclude that C, okay, is the answer because at least it has the same number of carbons. Okay, okay, so 22. Okay, build 1 in and build 2 in. Okay, treated separately with cold dilute acidified manganate ions. Okay, so basically this reaction, okay, this reaction condition here, okay, if we have the alkene, okay, the alkene will be added with, okay, two OH group, okay, alcohol groups. Okay, so it forms a diol. Okay, so okay, so we consider what happens there. Okay, build 1 in. Okay, so it's the double bond on the first carbon, 1 2 3 4. Okay, and then added 2 diols. Okay, added 2 um, alcohol group at the double bond. Okay, so added at these 2 positions here. Okay, so we expect it ends up like this. Okay, so okay, 1 2 3 4. Okay, so will be added at these 2 positions here. Okay, okay, so we can see that this one is secondary alcohol, this one is primary alcohol. Okay, so this one is matching with this description here. Okay, so that we know that X is correct. Okay, so okay, so without X we can exclude. Okay, we can exclude X. Okay, and then okay, both alkenes exhibit cis-trans isomerism. This one no cis-trans isomerism because it has the same group, okay, on both sides. Okay, so it has hydrogen and hydrogen. Okay, so if you have same groups on both sides, you don't have cis-trans. Okay, but butyl have cis-trans. So okay, the double bond on the second carbon. Okay, so you can have the trans version. Okay, and also the cis version. Okay, so it can have cis-trans. Okay, so when you have the diol added will be on these 2, okay, positions here. Okay, so here you will have so we know that this is incorrect, so basically at this point we can conclude that the answer is C. Okay, X and Y. Okay, to show that X and Y, the Y is correct, 2 secondary alcohol, so this is secondary and this is secondary. Okay, so this is also secondary. Okay, when we added with the OH group. Okay, so it will become secondary OH. Okay, so Y is correct. Okay, okay, 23. Okay, okay, 2 bromo 2 methyl pentene. Okay, tertiary halogenolalkane. Okay, so okay, so this condition here, hot concentrated ethanolic solution of sodium hydroxide. Okay, so under this condition, what we expect will happen is elimination. Okay, elimination reaction. Okay, so first we draw out the structure of this molecule there. Okay, so it's pentane. Okay, okay, so it's 5 carbon. Okay, 1 2 3 4 5. Okay, and then the bromine, okay, and the metal at the second position. Okay, so what will happen? Okay, so elimination will happen. Okay, elimination will happen at this position here. Okay, because this is the active site. Okay, because you have partial charges here. Okay, which makes this carbon center more reactive. Okay, so okay, so when the elimination happen, okay, so the okay, essentially the double bond can be positioned in two possible places. Okay, 1, 2, 3, 4, 5. Okay, the first possible position is here. Okay, so because it will form this okay, so basically it will form the intermediate, okay, which looks like this. Okay, okay, so the bromine will leave. Okay, so you have this carbocation here. Okay, so basically you have two possibilities. Okay, the double bond can form here, okay, or here. Okay, so that's why you have two possible products. Okay, okay, so this is the second one. Okay, okay, so this is corresponding to B. Okay, 2-methyl pen 1 in. Okay, so at the first position, pen 2 in at the second position. Okay, okay, polypropene. Okay, okay, so polypropene, the structure is like this. Okay, 1, 2, 3, 3 carbon. Okay, and then the double bond. Okay, so if you draw it in the format, okay, for polymerization, it will look like this. Okay, okay, so the format for polymerization, it will look like this. Okay, so imagine you have another molecule on the side. Okay, okay, so they can polymerize together. Okay, they can form bonding together. Okay, so essentially this will come here and then form single bond. Okay, single bond here. Okay, this pair of electron also will move to the next position. Okay, so essentially you are forming all single bonds. Okay, so we know that single bonds, okay, 4 single bonds, okay, around carbon. Okay, so this is sp3 hybridization. Okay, if we have sp3 hybridization, so means the geometry is tetrahedral. Okay, around carbon. Okay, tetrahedral. Okay, so means the bond angle is 109.5. Okay, so they are all 109.5. Okay, okay, 25. Okay, so alcohol, okay, has this formula here. Okay, it has several isomers. Okay, which one will form yellow precipitate with alkaline aqueous iodine? Okay, so this is a triiodomethane triiodol test. Okay, so it will detect a few things. Okay, okay, so it will detect ethanol. Okay, ethanol. Okay, methyl secondary alcohol. Okay, and also methyl ketones. Okay, so we check each of them. Okay, okay, so we know that these two is no, because this is primary alcohol. This is also primary alcohol. Okay, so this one is, okay, so this one is actually tertiary alcohol, butanol, 1, 2, 3, 4. Okay, and then at the second position you have the methyl, and then also the OH group. Okay, so this one is tertiary alcohol. Okay, tertiary alcohol because has 3 R groups. Okay, so this is a, okay, 1, 2, 3, 4. Okay, and then have the OH at the second position. Okay, and then the methyl at the third position. Okay, so this one is actually a secondary alcohol. Okay, so okay, so we don't have ketones here. Okay, Okay, so we don't have ethanol here, we don't have ethanol here, we also don't have ketones. Okay, so the one we want to see is secondary alcohol. So this is tertiary alcohol, so this is not. This is secondary alcohol, and then it has a methyl group. Okay, so this is the answer. Okay, 26. Okay, okay, so when we look at the okay, so this is ester. Okay, so ester we can form from two components. Okay, either acid, okay, ethanoate, or alcohol. Excuse me. Okay, so we know that, so we can pay attention on this. So the alcohol part will, excuse me, will form this O part here. Okay, so the acid will form the other part. Okay, so from here is clear. Okay, hexane, so means the alcohol part must have 6 carbon. So this one is 2 carbon, no. So if you count this one, this is 7 carbon, so also no. So this one is 6 carbon. Okay, so answer is D. Okay, okay, major product of the following reaction. Okay, so this is basically addition reaction. Okay, on the alkene. Okay, so when we have under this condition here, okay, so actually we will form okay, we will form carbocation. Okay, so we will form the carbocation, we will form the, because it's asking about the major product. Okay, so we know that the most stable carbocation is the tertiary one. Okay, so in this case the tertiary carbocation will look like this. Okay, so it will prefer, okay, to form this carbocation. Okay, so the bromine will come and react. Okay, 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 so this also have another option of forming the carbocation that is having the positive on this position and at this position here, but these are less stable. Okay, the tertiary one is the most stable. Okay, so we expect the product to look like this. Okay, okay, structure, how many chiral centers? Okay, so when we talk about chiral center, is the environment. Okay, 4 different groups. Okay, 4 different groups around the carbon. Okay, then we have chiral center. Okay, so 4 different groups or 4 different environment. Okay, so immediately we know that for sure this is not a chiral center because this is like CH3. Okay, so you already have 3 repeated, so definitely no. Okay, so if you see carefully, you will find that there are actually 7 chiral centers. Okay, so I will mark them here. Okay, so if you see carefully, all of them, okay, so the one that is not shown will be the hydrogen. All of them will have 4 different groups, okay, or 4 different environments, okay, around the carbon. Okay, so you have hydrogen and hydrogen. Okay, so in total there are 7 chiral centers. Okay, okay, so this one is about the interpretation of the infrared, okay, spectrum. Okay, so if you refer to the table, okay, the wave number table, you will find that this is corresponding to, okay, so this is around 2300 to 3000. Okay, so this is corresponding to the OH for carboxylic acid. Okay, and then this is corresponding to the C, okay, carbonyl group. Okay, 1700, and then this is corresponding to CO. Okay, So combining all of this information here, we can conclude that this is an acid. Okay? Okay, which reaction will produce organic ion with a good yield? Okay, so the answer is A. Okay, so because, okay, ethane nitrile, okay, CH3, okay, CN, okay, plus water, okay, so this is a hydrolysis reaction, okay, and sodium hydroxide, okay, so basically it will form something like this, CH3, COO negative, okay, and then sodium plus, okay, and ammonia, okay, so this is the organic anion, okay, so this is the organic anion form here, okay, okay, number 31, okay, okay, so okay, so we need to tell, okay, which combination, okay, corresponding to ABCD, okay. Okay, definitions of many chemical terms can be illustrated by chemical equations, okay. Which, okay, which one include formation of positive ion, okay. So ionization energy, yes, okay, because it's losing one electron, so it forms a positive ion. Heterolytic fission of covalent bond, okay, it's like when you have a covalent bond is unequal breaking of the bond, okay, where the pair of electron is exclusively taken by one of the parties, okay, so you end up with, okay, C plus and Br negative, so it forms this C plus carbocation, so it's yes. Okay, enthalpy change of atomization, no. Okay, so basically they separate into atoms only, okay, not necessarily will form positive ion, okay. Okay, so the answer is B, okay, for 1 and 2, okay. Which one has no over or dipole moment, okay, so boron trifluoride, okay, so 3 groups, okay, so it's separated, okay, with bond angle of 120, so it's very symmetrical, so it will not have overall dipole moment, although this is a polar bond, okay, even if it is a polar bond, if it is fully cancelled out by the symmetry, okay, so it still does not have overall dipole, okay. Methane, okay, so methane is also a symmetrical, um, okay, highly symmetrical molecule, okay, so the dipole moments also fully cancel out, okay, so it also no dipole moment, no dipole moment, no overall dipole moment. Phosphorus pentafluoride, okay, so phosphorus, okay, so 3 fluorine here, okay, so this part is symmetrical, all cancel out, okay, and then the up and down group also cancel out each other, so overall also no dipole moment, okay, so in this case the answer is A, okay. So Buckminster fullerene, okay, and graphene, okay, so graphene basically is a single sheet of the, okay, sp2 hybridized, okay, so it's the, okay, single sheet, okay, okay, so of this sp2 hybridized, okay, it's like graphite, okay, but it's single sheet, okay. Buckminster fullerene is this single sheet, okay, roll into a sphere shape, okay. So basically they still have delocalized electrons, okay, like the graphite, okay, because the one unhybridized, okay, orbital still can overlap, okay, so they have delocalized electrons, okay. Buckminster fullerene is giant molecular, so not really, because it's in a spherical shape, okay, so it does not go on infinitely, okay. So atoms in graphene is not tetrahedral, okay, So it's in the sp2 hybridized, so it's trigonal planar. Okay, so this one answer is D. Okay, only one is correct. Okay, 34. Okay, carbon monoxide burns readily in oxygen to form carbon dioxide. Okay, so in CO2 is +4, in CO is +2. Okay, so this is more stable, yes. Okay, because it's double bond. Okay, it's more stable. Okay, standard enthalpy change of formation for carbon dioxide is more negative than standard enthalpy change of carbon monoxide. Okay, because carbon dioxide is more stable, so also yes. Okay, equilibrium constant is likely to be high. Okay, because this is a very favorable reaction. Okay, so um, so it happens, okay, with a strong tendency. Okay, so equilibrium constant is the products, okay, over reactants. Okay, so we expect in this case the products will be high. Okay, so the equilibrium constant will also be high. Okay, so this is A. Okay, all of them correct. Okay, 35. Okay, so catalytic converters. Okay, so all these three, okay, will react with in catalytic converter. Okay, so NO2 will be converted to N2, unburnt fuel convert to CO2, CO converted to CO2. Okay, from harmful materials into non-harmful materials. Okay, but the one that will react with oxygen, okay, are 2 and 3 only. Okay, so carbon plus oxygen. So basically this is a combustion reaction. Okay, but NO2 will not react with oxygen. It's reduction. Okay, so it gets rid of the oxygen. Okay, so answer is C. Okay, 36. Okay, so this one, okay, we need to consider the oxidation state. Okay, so this one starting is 0 and 0, and then it becomes -1 and +1. Okay, so this one becomes -1 and +5. Okay, so first is okay, first is correct. Okay, requires higher temperature. Okay, because it needs to achieve a higher oxidation state, okay, of chlorine, so it needs more input of energy. Okay, so so in the first reaction 1 shows chlorine in 2 different oxidation states. Okay, correct. Okay, so there's a different 2 different oxidation states. Okay, so the products of reaction 2 show oxygen in 2 different oxidation states. So oxygen is staying the same. Okay, so number 3 is incorrect. So answer is B. Okay, 37. Okay, so which reaction is the organic compound oxidized? Okay, by the given reagent. Okay, so so this one is not oxidation. So in this case, okay, actually the product is hydroxynitrile. Okay, so it looks like this. Okay, so it's added with the OH group, okay, and the CN group. Okay, but this one is oxidation. Okay, so this one aldehyde. Okay, aldehyde oxidized to, okay, acid. Okay, carboxylic acid. Okay, so the answer is C. Okay, next. Okay, so this test here, so it's actually a test for, test for aldehyde. okay, and ketones, okay. So you will see the precipitate form, okay, in the presence of aldehyde and ketones, okay. So to form this aldehyde and ketone, this acidified potassium is dichromate is oxidizing agent, okay. So we need something that can oxidize to aldehyde and ketones, okay. So we expect that we are actually starting with alcohol, okay, because alcohol can oxidize to aldehyde and ketone, okay. Okay, so this one is actually a primary alcohol, okay. Okay, so it can be oxidized. Secondary alcohol also can be oxidized, but this one is tertiary alcohol. So tertiary alcohol is very difficult to be oxidized, okay. So because it's the carbon is already occupied with 3R groups, okay, so it has no other space to accommodate the carbonyl group in the aldehyde, okay. So the tertiary alcohol will not be oxidized, okay. So answer is 1 and 2, okay. So it's B. Okay, number 39, okay. So chlorofluorocarbons, okay, will be broken down by ultraviolet radiation, okay. So essentially we have the bond broken, okay. So actually we form the chloride radicals, okay. So chlorine radicals no, okay, because the CF bond is too strong, okay. Alkyl radicals also no, okay. So these are more involved in the halogenation, okay, halogenation reaction of alkenes, okay. So answer is D, okay. Okay, last question, okay, question 30, okay. So three isomers, okay, of the monomer, okay. So we can take a look, three possible isomer, okay. So we can have this, okay. So H on the same side, okay, H on the same side, and then okay, Cl, 2Cl on the other side, okay. And then the other one is, okay, when they are not on the same side, okay. Okay, so um, like this, okay. So you can actually tell, okay, this is a trans, okay, trans isomer, okay. And then you can also have the cis isomer, okay. Okay, Cl, H, H, okay. Okay, having this mixture of three isomers in the reaction mixture, is it possible to form these three products? Okay, so we can take a look. So this can be formed, okay, if you have, okay, one unit of this and one unit of this, you can form this one, okay. So no problem, okay. So this one, if you have, okay, um, let's say you have one unit of this, okay, and then you have another one, okay, one unit, okay, then you can form these two, okay, no problem. Okay, so this one, okay, when you have, okay, let's say you have this one, okay, you join together with another, okay, for example this one here, okay, so it works, okay. Okay, so all of them can be formed, okay. So the answer is A here, okay. So yes, so that's the end of the review for today. So if you like this video, give a like and subscribe, okay. I will see you next time. Bye.